In the previous class we were left with this equation. Now here check it, like I have assumed some equation and then I have formed this equation. Now here again we'll do some more assumption and simplify this. Like here, this part delta 1 minus delta 2, so I am assuming it as delta 1 minus delta 2 as delta. Okay, so this is the change, and one more quantity I am assuming as gamma, and that gamma is theta 1 2 minus pi by 2. Okay, so these two quantities I am changing it. So what I will get now, if I as you can see in this equation here, the delta 1 minus delta 2 is in the this form. So cos, you can write cos del minus theta 1, and this cos, if I put this second assumption, so I'll write it. So I'll write it like this: cos del minus theta, if I put it like this, so it's gamma minus pi by 2. Okay, so this is how. So you will, what you will get, in place of cos you will get sine del minus gamma. Okay, and similarly if we put in place of sine del minus gamma minus pi by 2, so we will get cos del minus gamma. So I'll just replace this equation with this term. So I will rewrite the previous equation like, I'll rewrite this equation like P1 is equal to E1 square G11 plus E1 E2 Y12 sine del minus gamma. Okay, del minus gamma, and for Q1 mod E1 minus square B11 plus E1 E2 Y12 sine, cos, it has to be cos del minus gamma. Now if you see here, there is a difference with our previous equation. So I have already told you that in the previous power system stability you have defined, for a two bus system you have calculated the power as EV upon XS sine delta, right? Now here there is some changes. Along with the sine term, you are getting one constant term also in the real power. Okay, so that is what the difference is. So the power angle equation which you are getting now, it has some constant term plus some sine term. Similarly it happens here also. In the reactive power equation you were getting that constant term, but in the real power you are not getting that term. Okay, and here we were assuming r as 0. Okay, now if you assume in this equation also as r equal to 0, what will happen that your G11, that is your susceptance, okay, will be, and susceptance and your gamma term, this will be 0. So you can put G11 as 0 and your gamma will be 0 if you are assuming. So your equation will transform from here, it will be like this. So this is nothing but our previous equation only, but sine delta. So this term only it is coming here. Okay, so I can expect this. This is my maximum term, P max. Okay, this is my P max. You can assume this as PC, this term, PC. This is the constant term. Okay, and your y12, sorry, y12. So here we can replace that y12 with your x term. Okay, so we'll do one numerical based on that, then you will get the clarity of the advantage of this. Okay, for if you increase the multi-machine system, you have to increase the number of buses will increase, but to find out the stability of transient stability, we will prefer going the method of this admittance matrix. Okay, what we have done in this like calculation, that we have calculated the current of one bus. Okay, and then we have done the power, and we have applied it into our power equation. So P plus JQ, and we have write that V into summation and some I star, right? We have done like this. So this analysis will make us compute our result more easily. Okay, rather than going to the swing equations, the swing equation will affect us, but here the analysis will be quite easier. Okay, so next we will check around one numerical, and then you will find out that why we are actually focusing on this. Okay, thank you. Okay, so this is the first equation or first numerical problem for our multi-machine stability system, and you have already solved this kind of problem in your power system stability, but we are going to revise that in this problem, and then we will modify this problem for our previous case, and then you will know the difference how I am analyzing our power angle equation. Okay, what's the difference? Here the question says that this is our system, and this system is a single line diagram, shows the transmission to a metropolitan system considered as an infinite bus. So here it already says that this is my infinite bus, so that itself means that the voltage will be 1 at an angle 0 degree. That's it. Infinite bus means the voltage is 1 at an angle 0, and the machine is delivering 1 per unit power, and both the terminal voltage and the infinite bus voltage are 1 per unit of power, 1 per unit. Okay, so this here the machine is delivering 1 per unit. So this 1 per unit means the machine is actually delivering the mechanical power is 1 per unit, PS is 1 per unit. Okay, so that is your 1 per unit. Now next, the both the terminal voltage and the environment, and now here the next term is the terminal voltage. So here if you see terminal voltage, that means the voltage comes here, this is the terminal ends of the generator. That means you need to consider this after this reactance, the terminal voltage, this is your terminal. Okay, so this is the terminal voltage, and the infinite bus is 1 per unit. So infinite bus we have already taken as 1 per unit. Determine the power angle equation of the given system. So here first we will draw our circuit. So this is our generator, and then this is our generator reactance. Okay, so this generator, this is my terminal, remember, this is my terminal, and then comes our, so I will not confuse you, I have made a bus bar. Okay, so this is, I need not to make this now straight line. I won't be doing making a straight line, because that makes us that make us say it's a bus bar. So here the bus system starts from here. Okay, and then you have two transmission line, this is one, and then this is one double circuit line, and then there is a one more infinite bus, that is your, so this voltage is 1 per unit, right? So here to here is 1 at an angle 0. Okay, this is your J 0.1, J 0.4, J 0.4. Here it is J 0.2. Okay, and this is our, and this is your VT, and this is your ET. Okay, so terminal EMF developed in a terminal is ET, and the terminal EMF outside means the sending end voltage that is coming out of your alternator, that is your VT. Now we need to find out first, we need to find out the power angle equation. Okay, so we need to find out the power angle equation. Before that, we need to deal with how much delta it is operating. Now if you check here, what we'll do, first we will be finding out the admittance reactance excess, what you have done in your power system stability. So you find out the excess with respect to here, between these two terminals. Okay, terminal voltage. So I will find out the excess between these two. So you can directly find out that this is, these two are in parallel, so it will give you 0.2, and this is in your series, so you can write it as J 0.1 plus J 0.4 upon 2, so that is your 0.3, right? So this is your excess. And if you have to find out the power, so delivering power is 1 per unit. So what I can say that the rated capacity without any acceleration is 1 per unit. So that is your VT upon V. You can say this is your V. So VT into V upon XS sine delta, and that is your, you can put it, so VT is 1 per unit, V is 1 per unit, XS is J 0.3, and sine delta, right? So you can calculate that sine delta, and it comes out to be, delta comes out to be 17.458. Okay, and this delta is the VT. Okay, this delta is because the power comes from higher angle to your lower angle. So here what I can say that VT is 1 at an angle 17.458. remember this. So that's why delta is positive here. If the power comes from higher angle to your lower angle, leading angle to a lagging angle. Okay, next is your uh, once I have find out this, I need to find out ET. Okay, because for our power angle equation, you need to go for your EMF voltage. Now what I have to do, I have to find out the ET part. Now if you have to go for ET part, you need to know the current. Now what I am going to do, how much current is flowing in this path. Okay, how much current I. So if you want to write the I part, I is the voltage difference between these two and divided by this. So what I can say, 1 at an angle 17.458 minus 1 at an angle 0 and divided by 0.3. Okay, so I think you will get 1 at an angle 1.018012 at an angle 8.729. Okay, so this is your current that is coming from here. Now take a loop here. In this, take a loop here. So what you will find, the same current will come from here also. Okay, so the same current will come from here also. So what you can write ET. If you want to write the KVL equation, you will get ET is equal to VT plus I into X, and X I think better to write at 0.2. So this X is nothing but your J 0.2, J 0.2. So this is our X. Just put it here with the values. VT you have already calculated. Put the I value here. You will get ET as 1 at an angle 1.0550 at an angle 28.44. Okay, now this is our ET. Okay, now if I find out the power equation, this power equation coming from your directly from the EMF. Now the previously power was coming from the terminals. Okay, output terminal. That's why I have referred it as output delivering, or you can say that the maximum that is coming out. What is actually getting in from power, that is here. So I am referring it as PE. Okay, PE is ET into V, ET upon V into X. Now this X will differ from excess sine delta. Why? Because now you have to include 0.2 also. Okay, J 0.2 also. So here ET is 1.050, V is 1, and if you include 0.2 from here, from this end to this end, now you have to include the X. So now X changes to 0.5, right? 0.5 sine delta. So you will get this equation PE as 2.10 sine delta. That is your PE. Okay, that is your PE. Now talking about the equation or your swing equation, what I can write? Swing equation was talking about your swing equation, and your swing equation was H upon phi f, right? H upon phi f d square delta upon dt square. Now what is our mechanical? That is our 1 per unit. What is our electrical? That is our 2.10 sine delta. Okay, that's the final equations. Okay, so this is what our equation comes. Now I am adding some more extra uh, uh, problems or in this numerical. Now let's suppose assume that there is a three-phase fault occurs at P. Okay. Now there is a three-phase fault occurs at P. Determine the power angle equation. Okay. Determine the power angle equation, and you do it by your own by any method what you have learned. I'll I'll make use of my explanation or theoretical explanation, that power equation, or by using Y-bus matrix I will explain you how we can do it. Now at the end I require the answer, that is PE. Okay, so PE during the fault I require this. Please comment it in the Google Classroom. Okay, Google Classroom, and that will determine how many of you are following, how many of you are following the lectures, okay, or on a regular basis. So I want this answer. Those who will see the video, they will comment, and those who won't, they won't. Okay, so those who have seen, please don't share the answer, or please don't tell people that sir have asked this question in the end of the lecture. Okay, so that will make me focus that how many of you are on a parallel path with me. Okay, so let's do it and give your answer. And there is one more problem that I have to clarify. I'll do it in the next class. Lot of people have got the problem with the bipolar part. I'll answer it. Okay, thank you.